R squared is the coefficient of variation, and it tells us if the model has strong or weak predictive model. For example, if R squared equals 80%, the model can predict or explain 80% of the change in Y. If R squared is larger or equal to 50%, it means the model has strong predictive power.
And now we are going to use the graphs to show and explain R squared. As we can see in the video, we have estimated some variables for y, which are 5, 10, 15, and 20. From 5, we have drew a line, which is called a regression line. And then from the 10, we have drew a horizontal line, which is called the y bar or the expected y. From 15, we have drew another horizontal line which is above the y bar, and we call it the y hat or the predicted y. Finally, we have drew a line which is above the y bar and the y hat, and it's called y or the true y. We can see that the difference between the y hat and the y bar is called regression or explained variation, and the difference between the y or the true y and the y hat is called error term or residual, or we can say in another term, unexplained variation. The difference between the true y and the y bar is called the total variation, and it's considered from the explained and unexplained variation. So let's recap what we have seen in the video. Total variation equals to the residual plus the regression, and we can write the total variation as the summation of y minus y bar squared, and the residual as the summation of true y minus the predicted y squared, and the regression as the summation of predicted y minus the expected y squared.
In order to prove that R squared equals 1 minus the residual over the total, we will do the following. First, the initial formula is the total variation equals the regression plus the residual. So now we are going to divide both sides by the total. So the first one is going to equal the total divided by the total, and it equals, after the equal sign, it will be the regression divided by the total variation plus the residual divided by the total. This will result in 1 equals R squared plus residual divided by the total. So the R squared will equal to 1 minus the residual over the total.
And now moving to e-views. As we can see, we can start with a quick estimation, and we can write the food expenditure, which is the y in our case, c, which is the intercept, and the x, which is the income. After that, we will press OK and we will have the results. As you can see here, the R squared is 0.31.7, which is 31.7%.
In our model, R squared equals 31.71%. That income can predict 31.71% of change in food consumption.
And it's less than 50%, which is, it has a weak prediction power. And now we are going to adjust this result. We will just add log before the y and before the x, and then we will press OK and see the results as well. As you can see here, when we use the log of the food expenditure, we resulted of our R squared equals to 0.40, which is 40%, and an adjusted R squared equals to 38.5%. R squared has two limitations. The first limitation is that it doesn't consider the number of variables, so we cannot use it to compare two models. The second limitation is that it doesn't consider the number of observations.
To overcome these two problems, we will use adjusted R squared. So the R squared will equal to 1 minus the residual divided by the n minus r, all divided by the total divided by the n minus 1.
So as you can see here, the results of log of the food expenditure, that the R-square has raised from 31.7% to 40%. And that's how we can overcome the R-square limitations.